Okay, so for the first problem, well, for me at least, it's for the first problem. I also agree that the answer is 1. So this will be the right answer. Okay. So any questions on this problem? Again, I'm not going over the work. For you to see how the question is done, I will do it in my office hours. If you stop by and say hello, I'll do some math problems with you. Okay, so if there are no questions, moving on to the second problem I have here. We want to determine which of these equations are exact. So you just want to take its partial derivative respectively. You want to differentiate m with y and show that n respect to x. They're both equal. Okay, so is the first one exact? So what do you guys think? Okay, all right. So yes. What about the second one? Okay. What about the third? So, so the third one is no. And the last one is yes. So the answer will be 1, 2, and 4. Okay, so that's for the second problem I have. For number 3, you have to do some work. So this is the one you had to actually go through the process of which method to use and then compute its general solution, right? So which method was applicable to this differential equation? Separable. So this looks like a nice separable equation. So if I separate them, just to show you a little work, cosine y over sine y dy is equal to 2x over x minus 1 dx, and then fill in the rest. And after you do that, you'll see that the correct answer is number 2. Yeah, I worked it out, so I know how the answer looks like. All right, so any questions on that? So again, let me know if you guys have questions while I'm running down the list. Number 4, so number 4 I had is tiny typo, and I know it makes a big difference, but what I had was y1 for the second option as well. So I had y1 and y1 are linearly independent. So Carolyn pointed out to me because that happened to be your first question. So thank you very much. I appreciate that. And then I made that note on my whiteboard in Blackboard so that you guys don't get confused, like y1 and y1 linearly independent. It wouldn't make any sense. y1 and y2 are linearly independent. So that was a typo I had, and I corrected it on my file. So suppose y1 and y2 form a fundamental set of solutions of the differential equation, second order. Which of the following statements are true? So is the first one true? The general solution is their linear combination. Yes. What about the second statement? Is that true?
Yes, that's true.
Right. So I didn't emphasize a lot on linearly independent, but I'm assuming if you did the homework on web work, it gives you tons of problems what it means solutions to be linearly independent. Okay, so that was kind of like a homework questions. What about the third statement? They're not multiple of each other. Is that true? Right, so Sadia says that's also true. Yes, so if they're linearly independent, that means they're not multiple of each other. If they're linearly dependent, then they could be multiple of each other. Now, what about the fourth statement? Their Wronskian is 0 for all values of t. Now, if they're forming a fundamental set of solution, that means the Wronskian is never 0. So from that statement, we know 4 is not true. Okay, so the correct choice will be 1, 2, and 3. Okay, and moving on to number 5. Go ahead. No, I wouldn't ask for work for a theoretical question. So if you didn't show me work for 4, that's okay. Uh, yeah. Yep, absolutely. Absolutely, yep. So if you show me work, that's great. But for theoretical question, it's just thinking about them. So I wouldn't want you to write down what you're thinking, but if you want to, you could. Okay, so that's okay if you didn't show work. I will still give you credit if you chose the right choice. Okay, so moving on to number 5. So here we want to define the Wronskian of the pair of two independent solutions. So here I want you to use Abel's theorem because we don't know what are the solutions, right? We just know we have some y1 and y2, and we want to compute the Wronskian. So that would be Abel's theorem. Wronskian will be c times e to the integral of negative p of t dt. And then you have to correctly identify which one is p of t. So so Leona says y is in this one too. So let's check. So if I were to plug in p of t, well, first you need to write this in standard form, right? So this would become y double prime minus 4 over t plus 1 y equals 0. So then the Wronskian becomes c times e to the integral of negative, because p of t is this function right here. That's p of t. So it would be positive 4 over t dt. And if I integrate this, this would be c times e to the 4 ln of t. And then by laws of exponents, I can bring 4 as an exponent for t, and then e and ln will cancel out. So that would be t to the 4th power. That would be the Wronskian. So by doing it carefully, 3 would be the correct choice. Okay? All right, so I hope that answers your question, Liana. Okay, so you see it. Right, so if you fall for the trick, you're gonna get the wrong choice. So that's why multiple choice exams are always, sometimes they're tricky, right? They kind of give you the answer, but it's not the right answer, it's the wrong answer. So here, yeah, I would say my choices were a bit tricky. So be careful. Go ahead. Yeah, I will give you a partial credit. Mm-hmm. So for every question, you will get partial credits. So I will be taking points off. I will be giving points out. So nothing is settled yet on Blackboard. So that's why I'm going to modify all the grades. So, okay. Someone else have a question? I think someone else had in hand and I missed it. Okay. All right. Okay. So moving on to the next question. Oh, this is a slow field. Oh, this was pretty. Did you guys like it? Mm-hmm. So, right. So if you look at so you always want to find clever ways to answer this question. We want to know where is the slope 0 and where is the slope undefined. Those are the giveaway points, right? So if you look at it, on the x-axis, where y is equal to 0, there's no slope, right? So that means it's undefined. So that means the only choice that gives you undefined when y is equal to 0 is this guy right here. And then another way to see where is the slope equal to 0. So in this graph, our slope is equal to 0 right here. These little tiny horizontal lines. So you'll get slope equal to 0 when x is equal to 0. So it couldn't be the 4th because that's when the slope is undefined. So you can eliminate 4, you can eliminate 1 and 2 also, and third one will be the option. So that will be one way to pick an answer for slope field. Another way would be to just pick some random values, plug them in, and see if the slope matches. Okay, so a good point will be to pick, say, 1, 1, and then see if you get this slope right here, which is sort of like a positive slope, increasing, right? So that's another way to test, but I would say go with undefined slope, horizontal slope, and so on. So that would be the answer to this question. I kind of like this problem a lot. It was very pretty, very graphical. It gives you a view of how slopes of first order looks like. So that was nice. Number 7. So for number 7, you had to do a lot of work because it's worth 12 points, and we had to run through reduction of order because that's the method I want you to use. So if you run through reduction of order, what are the answers you guys got? If you remember. Yeah, that sounds right. So y1 is given. Yeah. Mm-hmm. So I think that's the right answer. Someone else had a question? Go. Uh, it's considered wrong because we just want the solution. We don't want multiple of solutions, right? But of course, you're getting partial credits. I will see how much I will take off based on how much work you do. Okay? All right. Okay, so that was a lot of points. That's 12 points. So that was a good 12-point question. Next, number 8. This was another solving problem. So you want to compute the general solution for this second order homogeneous. So what kind of roots do you get for this characteristic? So we have 9r squared minus 30r plus 25 equals to 0. And then you can factor this, right? So 5 over 3, repeat it. All right, so if you do that, this would factor into 3r. So, all right, so guys, let's pause for a few seconds. I think my stylus stopped working. So let's take a break for like just a minute, okay? I'm gonna be back in less than a minute. So. Okay, I'm back. So let's, sorry, that was unexpected. So you all had the same question but in different order, okay? And your choices probably randomized as well. So this is 3r plus 5, no, minus 5 would do. And then 3r minus 5, so we see r is equal to 5 over 3 repeated, okay? So the correct choice would be which one? So what do you guys think? So Musa says correct choice is 2. Yep, that's absolutely right. And number 9, here's another problem you want to solve. and then you want to evaluate this value of the solution. So what did you guys get for this one?
I got -2 times e to the 4 pi.
Yeah.
Which is option C.
Yeah, this looks right. It looks familiar to me. So I would go with that one. So this was another question that requires more of your time than the other questions. So when it comes to solving, they're worth more because they require more time. So I try to put it that way. This one, you didn't really have to do a lot of work. You just have to determine what is the integrating factor for this given differential equation. So you have to know the formula and just plug it in. So what's the correct choice for? So Aisha says x to the power. Yeah, right? So we know mu of x is equal to e to the integral of p of x dx. So in this case, p of x is this function right here. That's p of x. So we have e to the integral of 3 over x dx, which is x cubed. So yep, absolutely, that's the answer. And the last problem, so here is something to test your knowledge on something from the past, knowing the domain of cotangent. Do you guys remember that?
Domain of Cotangent is any real number, but except x cannot be, or whatever variable is not equal to pi times n.
Right.
Different numbers.
Right. So for every integer multiple of pi is where you have asymptote for cotangent. So every integer of pi, we have asymptote. So for question 11, you have to determine what is the domain of p of t, q of t, and g of t. So you want to put this in standard form. So we have y double prime plus e to the t over 1 minus t, y prime plus cotangent of t over 1 minus t times y is equal to t squared over 1 minus t. And now you want to determine the domain for this function and this function and this function. And you intersect them because you want them to be continuous. And then you see which interval you can see where the initial point fit into, because that's what the uniqueness and existence theorem will guarantee, a solution, a unique solution. So the domain for this function is all real numbers except 1, right? So you have to take out 1 from the domain. The domain for the next one, that's going to be a bit tricky because you're removing, so again, it's all real number except integer multiple of pi is where you have to take out from the domain. So n is any integer, right? So if n is equal to 1, so it's pi, n is equal to 2, you have 2 pi. All those points are removed from the domain, and you're also removing
t cannot equal to 1.
right, because of the bottom.
T cannot equal to pi times n, and also cannot equal to 1.
Right.
So the interval should be 1 comma pi n, whichever of integer you choose.
Right. So this one also r take away 1. So that means our interval that we're looking at where t naught is equal to 2. So if I were to write this domain out in interval notation and let n run some values of integers, we have, say, 0 to pi, that's 1, and then pi to 2 pi, and well, where's 1? Well, we know pi is 3.14, right? Are you guys following me? So 1, and then pi is 3.14, so it's bigger than 1. So this is 1 pi, this is 2 pi, and we have negative pi, and so on, right? So I think this way is better to understand. Now, t naught is equal to 2, Well, if pi is approximately 3.14, that means 2 will be somewhere here. So that means the interval that we guarantee to have a unique solution is on the interval from 1 to pi. So this will be the correct interval. Okay, so the correct choice for this question would be 1 and pi. That would be the answer. But you kind of have to look at each pieces first and then decide where does the initial value contain, and that will be the interval we're guaranteed to have a unique solution. Okay. All right. So that was it. So that was your short 1 hour exam. 1 hour, a little bit more. Any questions? Okay. So if there are no questions, let's move on to 3.5. So today we're going to do more exciting stuff because differential equations are always exciting. So I cannot give you more time because for so many reasons. But I think these questions, if you practice every day, just little by little, you'll get used to it and you'll kind of know what to do. So, but you just have to understand how the theorem works, and you have to be very strong with your algebra because all of these questions require algebraic technique. So depending on how many questions I come up with for the next test, I will determine the time. But you'll have the same range of time for the second test as well. Okay. So again, please learn how to time yourself and just know how you can do well. And I think you guys did well. I just haven't looked at the work yet, but I'm going to look at it and I'll see how you guys did. So for this test, I wouldn't say time was the issue, it's knowing the materials. Because the only ones you had to solve were number 3 and then number 7, 8, and 9. So there's only 4 questions that you really had to solve. So you can put maximum of 10 points, 10 minutes for each question, and then the rest you can spend thinking about the remaining questions. So they're not really solving, they're just thinking through the question. So again, I would really strongly encourage those of you whose time was the issue, just do a lot of practice, do your homework, do the recommended textbook question. That's the best way you can prepare for a math test, okay? So let's see how you guys do for the next one. And we have a quiz coming up next week, so let's think positive and move forward, right? So this is over. Let's not think about it anymore. Yeah, so the reason you can't skip a question or move on to the next question without finishing the question you're on, it's again for security purpose. So I just want to make sure everyone gets that. Okay. All right. So enough talk about the test. Let's learn something new today. So again, if you have more question or concern, come by my office hours. I'm here and nobody's here. I'm always here, but we can chat more during office hours. Personal questions, personal concern, office hours. Okay. All right. So having said that, let's move on to the next section. We're on 3.5. So 3.5 is a very interesting section. They all are. Yeah.
I was looking at the syllabus, and there's a section called 3.3/3.4 is Cauchy-Euler's equations.
Mm-hmm.
Are we going over the section?
Send me an email. I'll look it up. Yeah. So 3.5, we're going to do non-homogeneous equations. And we're going to learn the method called undetermined coefficients. So the method of undetermined coefficients. So we're solving second order linear differential equations with constant coefficients, right? So this is the method for non-homogeneous equation. So far we know how to solve homogeneous, meaning when the right side is equal to 0. So far we know how to solve say a y double prime plus by prime plus cy equals to 0, right? Where g of t is equal to 0. And we looked at its characteristic polynomial, and we saw that we can have three different scenarios where the roots are real, distinct, we know how to write the solution. When the roots are real and repeated, we also know how to write the solution. And if the roots are complex, then we also know how to express the solution for complex roots. Now we're going to add one more factor to this, meaning now g of t is not going to be 0. Okay, so suppose we have y double prime, so let's take the same equation. Suppose we have a times y double prime plus by prime plus cy equals to a function g of t. So some function g of t, and I'll restrict g of t as we go on, where p of t, well, there's no p of t here, where a, b, c are real values and g of t is continuous on some interval I. Okay, and strictly g of t is not 0, because if it's 0, then it's homogeneous. We know how to find solutions. What if it's not 0? What if it's some random functions? Can we still seek to find the solution to this? And the answer is yes. So the question is, so here's the big question. So I always like to put a big question. The big question is, how do we construct solution to non-homogeneous differential equation? Okay, so well, here's how we're going to do it. We're going to use the method of undetermined coefficients. Okay, so let me give you the steps how the method works, and then I'll explain it through some examples for different scenarios for g of t, and then I'll give you an outline how to pick your solution if g of t is such and such function. Okay, so that's what I'm going to do. So here's the idea for solving differential equations. So this is particularly the undetermined coefficients method. So the method of undetermined coefficients. So this is a very specific method. Okay, so the first step for using this method is to find the solution to the corresponding homogeneous equation. So we're going to call that y sub h. Y little h, meaning that's the solution to the homogeneous case. Now the second step, once you have computed the solution to the homogeneous portion, the second step is to, based on two things. One, based on the function g of t that's given to you initially in the equation, and the second will be yh, which we just computed on the first step. We will guess a form of the particular solution, which we're going to call it yp. In our textbook or on WebWork, it's going to call it y of t, big Y of t. But I like to use y sub p because it's a particular solution, so the notation is very useful. So there's no lambda in my writing. This is yh, which is the homogeneous, and this is y of t, y of t. So, sorry, sometimes it's weird, right? All these symbols, and then when I write it, makes it weird. All right, so based on the given g of t and based on our computation for the homogeneous case, we will guess a form for the particular solution, which is denoted by yp, so that when you plug in yp to your initial equation, so you have a times yp double prime, right? You compute its first and second derivative, plus b times yp prime plus c times yp. It's going to equal g of t. And that will allow you to solve for your undetermined coefficients. Okay, so that's where the name of the method comes from. Now, here is something to keep in mind. This is very crucial, that yp, the particular solution, must not be same as yh, meaning the homogeneous solution. Make sure they're independent, okay? And I will show you how to make them independent if they happen to be the same. The last step is to write out the general solution. So the general solution, it's going to be y equals, so it's going to be homogeneous solution plus the particular solution. So that would be our solution to the non-homogeneous differential equation. Okay, so this method is very specific. Now, when can we use this method? So here's a remark. So if g of t happens to be the following function, okay, 1, so exponential, right? So meaning if you have e to some alpha t, right? If you have an exponential, you can use this method. Second, if it's a polynomial, you can use this method. Polynomial, I hope you guys remember the form. P of t is some a n t to the n, where n is greater than or equal to 0 and integers. Right? So that's how we represent polynomials of nth degree. And then last case for g of t would be if g of t happens to be sine, let's call it sine at or cosine at. So if g of t happens to be an exponential, polynomial of nth degree, and sine or cosine, then you can use this method. If it's other functions, like for example secant or tangent, we have another method which we're going to study in 3.6. Okay, so that's going to be more general method. But this is very specific, it's nice and very clean. So let's see how it works. Okay, so before I show you how the method works, let me just prove this statement to you, the last statement, where I'm calling the general solution to be the homogeneous portion plus the particular solution. Why does that work? So here's the proof for third statement. So again, proofs are nice. They're they're entertaining, but you don't have to know much of it for this course. But understanding it is very important for you moving on to the next course. Okay. So here's a tiny proof. So very tiny of 3. So statement 3, where we consider our general solution to be yh plus yp. So let y be a general solution to the differential equation, which was y double prime plus, let's just bring these functions in, p of t plus, oh, all right, guys. Okay, back. Q of t times y is equal to some function g of t, right? So that's the differential equation we're working with. So let yp be a particular solution. Then let's note the following, okay? So I'm going to say that y minus yp is the, so this is the claim, okay? That y minus yp is the solution to the homogeneous case, okay, meaning yh. So that means if that's a solution, that means I have to compute its first derivative, second derivative, plug it in to this statement and see if it holds, right? So the usual drill. So let's do that. So we have y minus yp to the second derivative plus p of t times y minus yp to the first derivative plus q of t times y minus yp is equal to let's hold on to the equal sign, but it's going to be equal to g of t. So if I do that, what do I have? We have, so differentiation is linear, so I can differentiate each term, and then I'm going to group them in this way. So I have y double prime plus p of t. For the second term, I can differentiate once, so I have y prime, and the third term I'm going to differentiate, no differentiation, so just multiply q of t. We have q of t times y, and then plus, well, not plus, it's going to be minus, because minus yp. So minus yp double prime minus p of t times yp prime minus q of t times yp. Okay? Now I'm just going to pull the negative out and then factor these. So this is how it looks like. Well, now, what is this equal to? Well, that was the original statement, right? So this is equal to g of t. And then this is also in the form of g of t. So minus g of t. So what is this eventually equal to? 0. So we see that if we assume that the y minus yp is a solution to the homogeneous case, that means the general solution would be the homogeneous plus the particular. Okay, so that would be the next statement. So this means that y minus yp is, let's say, solves the homogeneous case. So that means y minus yp is equal to yh, because that's how we denote homogeneous, and therefore we claim that y, which is the general solution, it's going to be yh plus yp. And that was the claim we wanted to prove. Okay? So that's the proof of statement 3 that we claim over here when we're writing down the steps. Okay? All right. Now let me show you how this method works with a couple of examples, and then we will write down a general step for undetermined coefficients. Any questions so far? Okay. All right, so let me scroll up a little bit. So okay, so let's do an example. Okay, so lower. Okay, so here you go.
Sorry.
It's okay. All right, so while you copy that, let me write down an example. So here's an example. So let's solve y double prime minus 3y prime minus 4y equals to 5e to the negative t. Okay, so let me give you a heads up. This method is long, okay? So you really have to speed up your algebraic skills. And the next method we're going to study, it's also long. So make sure you just practice. Okay, so let's see how we can construct the solution to this non-homogeneous case. Okay, so the first thing is to compute the solution to the homogeneous, right? So the corresponding homogeneous equation to this, so let me write down step 1. So first we're going to find YH, which is the homogeneous case. So the corresponding homogeneous equation to this would be y double prime minus 3y prime minus 4y equals to 0, right? You just said g of t equal to 0. Now find its solution, so we write out its characteristic polynomial from before. So that would be r squared minus 3r minus 4 equals to 0. And now here you can run into any of those three cases that we studied. Now this one looks like nice factorable. So we have r minus 4, r plus 1 equals to 0. So we have distinct root. r1 is 4, r2 is negative 1. That's nice and neat. So our homogeneous solution, it's going to be c1 e to the 4t plus c2 e to the negative t. So that's YH. Now what was the second step? The second step is to, based on g of t, based on YH, we're going to guess the form of the particular solution. Okay? So this is the time when you want to guess. So let me show you how you're going to guess. So our g of t, so I should box this. So here's the solution to the homogeneous. Okay? So step 2, we're going to guess yp. So before we do that, let's analyze. G of t happens to be an exponential, right? So 5e to the negative t. Okay. And our homogeneous solution, well, it has exponentials, right? So, okay. I'm going to guess that yp will have the form of an exponential, right? If g of t is an exponential, the form you're going to guess will also be an exponential. But you see how you have exponential, but times a constant. 5 is a constant. So I'm going to put an arbitrary constant. Let's call it a. So a times an exponential, e to the negative t. Okay, so that's the guess I have for yp. But I have to make sure that, so here's the box I had, that make sure that yp is not the same as yh. Meaning, whatever you guess is, make sure it doesn't appear in your homogeneous solution. Now, does this form appear in my homogeneous solution? Right? So if you look at this one and the yp that we just guessed, they're exactly the same function but just differ by a constant. So that's a problem. So we're going to modify it. We're going to modify it by multiplying it by t. And that's going to make it independent of the homogeneous solution. Okay? And now you check, does this appear in my homogeneous solution? Well, it doesn't, right? There's no more function in the homogeneous that looks like t times e to the negative t. So this is really at e to the negative t. So this doesn't appear in my homogeneous solution, so that will be the form for our particular solution. Okay, so any questions on this? Now, this is very important that you understand how to determine the form of this particular solution. So that means once you've found your particular solution, you're going to compute its first derivative, second derivative, and you plug it into the original. That's the next step. So we found yp, so now let's find yp prime. So that's going to be done by product rule because t is a function. So we have ae to the negative t minus at e to the negative t. Okay, and now we compute its second derivative. So we have negative a e to the negative t, and then for the second one we use product rule again. So that would be negative a e to the negative t plus at e to the negative t. And then I can combine the like terms from the first two. That's negative 2a e to the negative t plus at e to the negative t. So I have an expression for yp, yp prime, yp double prime. And these are the expression I'm going to plug in to my original equation so I can solve for my undetermined coefficients, which is a in this case. So there's only one coefficient. Let me know if you guys have questions. I'm going to go ahead and plug in. So plug in yp, yp prime, so, and yp prime, so yp double prime into the, let's call it given equation. So the given equation was y double prime minus 3y prime, so we have y double prime, so that would be 2a e to the negative t plus at e to the negative t, and then minus, we had 3 times y prime, so that would be 3 times yp prime, and 3a e to the negative t plus 3a e to the negative t. Oh, I forgot a t, so. And then the last term we had negative 4 times y, so this is going to be negative 4 times yp. That would be at e to the negative t equals to g of t. Well, g of t is 5e to the negative t. I think that was the function. Yep. So that's the next step. And now the last thing is to compute what is a, and then we have our general solution. That will be step 3. So again, do some more algebra and then we have the answer. So I'm going to go ahead and try to combine like terms. Okay, so guys, help me out. So we have like terms here. That's negative 5a e to the negative t. And then the others are also like terms. So 3a and 4. Okay, so the 3 terms left over, they cancel out. So this is equal to 5e to the negative t. Are you following me? Are you guys following me? Okay. So let's continue. So that means if I equate the coefficients, I have negative 5a is equal to 5, which means a is equal to negative 1. So there we have it. And now we plug this into our yp. So we have a is equal to 1, negative 1. So that would be negative 1 t e to the negative t. So what is our solution to this? So step number 3, our solution, the general solution to this non-homogeneous, it's y equals yh plus yp, and we have all pieces. Yh was this purple box, c1 e to the 4t plus c2 e to the negative t minus t e to the negative t. So that's our general solution. So any questions on this? Alright, so we went through the entire process solving this.
Professor, can you explain again how you guessed YP?
So here, to guess yp, we look at g of t. So in this case, g of t is exponential. That means yp also has to be exponential. So the reason they have to match up the same group, meaning group function, because when you're differentiating, somehow some of the term will cancel. So that was step right here. We saw how some terms cancel out, and then we're able to equate the coefficient on both sides. That's why the function that you guess has to match your g of t, the form of that function. So we said, okay, it's going to be some constant a times e to the negative t, because e to the negative t involves in our g of t. Well, now you look back, now does this function appears in your homogeneous solution? And we said yes, because we have c2 e to the negative t. That's exactly the same function that we just guessed for yp. Now, to make both of them independent, we multiply them a function of t. So we have at e to the negative t. Now check this out. If you had, say, c3 t e to the negative t, right? So suppose you had that term there, and you guess your particular solution is still a e to the t, negative t. Well, then if you multiply by t, it's going to overlap with c3 e to the negative t, right? So that means you have to multiply by another t. So you would multiply by t squared to make it independent from the third solution from the homogeneous. So just like that, you'll keep multiplying by t, t squared, t cubed, depending on how many times does it match with the homogeneous solution, because you want to make it different from the homogeneous solution. Okay, does that make sense?
Yeah, it does. Thank you.
Okay, so let's do a couple more examples. But for next few examples, I'm not going to run through the entire calculation, because I think once you know your form, the correct form of yp, the rest is computing the derivatives, plug them into the original, collect like terms, equate the coefficients, solve for the undetermined coefficients. So that's algebra. You can fill those in. Let's do another problem where we're going to guess the form of the particular solution. So let's try this problem. So here is example 2. So I'm just going to modify. What if we have, so let's take the same differential equation, y double prime minus 3y prime minus 4y equals 2. Now I'm going to change g of t, okay? So I'm going to put, let's say, negative 8 e to the t cosine of 2t. Actually, let's hold on. No, not yet. We're going to do this after this problem. So let's backtrack a little bit. Let's do 2 sine of t. Okay. So we just want to find just the form of yp. Just the particular solution. So that means you still have to run through the steps, find the homogeneous solution, then determine the form of the particular solution. So we already know how the homogeneous solution looked like, right? We computed. This was the previous problem. I just gave you the same problem but different g of t. So we know yh. That was c1 e to the 4t plus c2 e to the negative t, right? So you do the work usual and you get to that step. Now yp, well, we have to guess, right? Now what is g of t? G of t is right here. So that means it has a trig function and it's sine. Okay, so this is how you're going to guess for g of t. If g of t is sine or cosine, your particular solution will have both sine and cosine. Okay, so I'm going to guess my yp is going to be a constant because of the 2 in front of sine. So let's call it a sine of t plus another constant b cosine of t. That's my guess for the particular solution. Again, because it involves sine, your particular solution has to involve sine and cosine. Okay, so so the reason it needs both functions, sine and cosine, is because when you differentiate sine and cosine, they just alternate, right? One time you have sine, another time you differentiate the cosine, and then negative sine, and then cosine, negative sine. So it just alternates between sine and cosine. That's why when you're guessing g of t for sine or cosine, you have to have both sine and cosine. I hope that makes sense. Let me know if you guys are confused. Are we good so far? Okay. Now is the time you're going to decide, does this appear in my homogeneous solution? If it does, we have to modify it by multiplying by t. Does any of this function overlap with the homogeneous? No. So that means that is the correct form for yp. Now if you want to think of it this way, you can say, okay, you can multiply this by t to the 0 power. Meaning you don't need to modify it. So it looks silly to write t to the 0. So just say no need to modify. Okay, so our yp will just be, so the form is going to be a sine t plus b cosine t. Okay, so that will be the particular form. And then to actually find these unknown coefficients, a and b, you just have to go through its derivatives, first and second, plug it back in, and it's going to be a long way to solve. So you can do that as a fun exercise. So if you do happen to work this out later, you will see that. So just test your algebra skill. You'll see that a would be negative 5 over 17, and b is going to be 3 over 17. So those are the unknown coefficients. Okay, so if you work it out, make sure you get those coefficients correctly. Okay, so let's determine particular solution for another example. So what if, right, what if we have y double prime minus 3y prime minus 4y equals 2. Now again, I'm going to switch around my g of t, negative 8 e to the t cosine of 2t. Okay, so I want to find the form of yp. Okay, so I'm going to give you just a few seconds to think about this based on the examples we just did. I think you can have a good idea of where to go with this one. Okay, so the usual way you would solve for the homogeneous, but we already know from before it's the same homogeneous I gave you, the same second order. So we already know yh is equal to the same function c1 e to the 4t plus c2 e to the negative t, right? That's from before. So let's guess what is the form for yp. This is my g of t. So what does it involve? Well, my g of t involves an exponential times cosine of 2t. So first thing should click in your mind that, oh, you have cosine, so that means you need sine and cosine to come along, right? They have to come along for your yp. Second thing is you also need e to the t, because that also multiplying cosine. And then you also need a constant to replace negative 8. So we're going to need constant times e to the t, cosine of 2t, plus another constant times e to the t times sine of 2t. That will be the form we're going to guess. So we have a e to the t cosine of 2t plus b e to the t sine of 2t. That's my guess, because it has to correlate with the g of t that you're given. Any questions? Now let's check. Does any of these function appear in my homogeneous solution?
Yes.
Which one?
The AE to the T sine 2T.
Well,
Like there's a constant.
my homogeneous solution is this, right?
No.
No. So, okay, so you see how the homogeneous is different from our guess. So the way you're guessing is you're matching up the form for g of t. So g of t is an exponential times cosine of 2t. So that means your guess has to involve an exponential times sine and cosine. Okay, so that's how I got these two guys right here. And now the next thing is you need a constant, unknown coefficients, to cover up negative 8, because that's a polynomial of degree 0, which is a constant. So that's why we need a and b. Okay, does that make sense? So it will make more sense as you work through different type of problems. So the first one I did was just plainly an exponential. I said, okay, here you have e to the negative t, so that means your guess should be a constant times e to the negative t, okay? And then the second one I gave you was sine of t times a constant. So that means your guess has to be sine and cosine times constants. That's why we guess this one to be yp. Now here I said, oh, what if I put an exponential and trig function? So that means your guess has to involve exponential and trig function, both sine and cosine. It doesn't matter which one you have for g of t, you need both sine and cosine, okay? All right, so, and then the rest will be solving it. You will compute its first derivative, second derivative, plug it in, and you get the idea. So let me write down the rule in a table, so that way you have it in more organized form. Okay, let me know if you guys have any questions so far. So here's the table for the method of undetermined coefficient. So we choose yp, which is the particular solution, to be the form based on the following. Okay, so this is a table just putting all the functions as a general function, so not a particular example, but in a general form. So if g of t happens to be such and such, what we're going to pick, and if this is the table for picking yp. Okay, so okay. Okay, so it looks straight to me. It's probably not so straight line, but okay. So if g of t is a polynomial, 1, so if it's a polynomial, so generally we would write polynomial of nth degree in this form. Pn of t is equal to an t to the nth power plus an minus 1 t to the n minus 1 all the way up to a0, right? That's a nth degree polynomial. So this is an nth degree polynomial. So if g of t is a polynomial, then you're going to guess your yp to match it up. So it has to be in the same family of function, meaning it has to be also a polynomial of nth degree. Okay, so your yp will also be a polynomial of nth degree. So you'll have an t to the n plus an minus 1 t to the n minus 1 all the way up to a0. Sorry, I should put a big a0. Okay, so that's the nth degree polynomial in standard form. Now, if any of these terms repeat in your homogeneous solution, then you would multiply this by t to the some power s. Okay, where s, so here, s will run from 0, 1, 2, and so on. For example, when you saw this one right here, I put t to the 0th power, meaning s is 0, which means I don't need any t to modify the particular solution. Whereas in this example, I have yp is equal to ae to the negative t times t, and you can think of s is 1 because I need just one power of t to modify this solution different from the homogeneous. So it can vary from 0, 1, 2, 3, and so on. Okay, so that's what the t to the s means. So here s is equal to 0, 1, 2, and so on. That will ensure that no terms in yp is a solution in solution of the corresponding homogeneous. So that's what t to the s power would do. It will make it independent from the homogeneous solution. So we will do this for every cases. So that's the first case. Now let's look at the second case. When g of t is a polynomial and exponential. So that means the form of g of t you're looking at, it's some polynomial times e to the alpha t, meaning exponential to some power. Okay? So if that's the case, that means yp that we're going to guess has to match up this form of g of t. So you're going to need a polynomial of the nth degree to match it up, and you'll need an exponential to the alpha t. So your yp has to be a polynomial of nth degree times exponential times to the alpha t. And to modify this, again, we do t to the s power to make it different from the homogeneous case. Same explanation. And then the last case that we have, so sorry guys, these lines I'm drawing, they're not straight. I can't draw straight lines for some reason, so it's not straight at all. So the third case we have is polynomial, exponential, and sine or cosine. So you can have either sine of some bt, that's just an angle, or cosine of some bt. So if you have this case, so that means we're looking at a polynomial of nth degree exponential to the alpha t times either sine, so you can have sine or cosine. If that happens to be your g of t, that means our guess for the particular solution, it also have to match up, right? It has to be polynomial of nth degree exponential to the power alpha t and cosine and sine. So we will have some polynomial of nth degree times exponential to the alpha t sine of bt plus another polynomial, so let's call it q of n t plus e to the alpha t times cosine of bt. And if any of these appear in my homogeneous solution, I need to modify it, so we multiply it by t to some power s. That would be the modification. Okay. So there we have it, all different cases if yp, if g of t is such and such. So that's the table that you should remember how to pick yp. Okay. So let me give you an example. Okay. So let's put an example for all of these. So let's look at the second case. Okay, where you have so say you're looking at a g of t that happens to be t squared plus 4 times e to the t. Suppose that function happens to be your g of t. So what is my yp? So someone tell me, what do I need for yp to match g of t? All right, are you guys there? Hello, can you guys hear me? Okay, so answer this question. And it's okay if you get it wrong. I don't really mind. This is a learning experience. So if you want to give me a wrong answer, give me a wrong answer. We learn from each other, so why not? So Sadia says t squared. Yes, that's part of it. So think, Sadia. We need t squared. Well, we don't need just t squared. T squared plus 4, that's a second degree polynomial, right? Because you can say this is a t squared, right? Plus 0t, because we don't have t term, plus 4. So it's a second degree polynomial. So if I were to write it in a general form, we have a second degree polynomial, so that's a t squared plus bt plus c. So you always want to write it in general form. That's a second degree polynomial. So I need a second degree polynomial. Got it. What else do I need? E of t. So I need the second degree polynomial times e of t. So e to the t. So that will be my form for yp, my guess. Now I'm going to have to modify this by multiplying by t to the some power s. S will be depending on what I have in my homogeneous solution, right? So because I don't have a homogeneous case here, I'm just writing out the form, we will just leave it as t to the s. Any question on this? Okay. All right. Okay, what about the last case? What if you have, say, so let's do t cosine of 40. So someone tell me what would be a possible form for yp.
It's going to be at cosine of small bt plus uppercase bt sine of, I guess, lowercase at.
So you're almost right. Thank you. I really appreciate that. You're almost right. But what's the general form of a first degree polynomial? So t, this is a first degree polynomial, right? What is the form of a first degree polynomial? Do you guys remember this? Right, so Liana, it's t plus c, right? So, well, t will need an unknown coefficient. So I'm going to, because if you don't, then it's assumed to be a 1. So we're going to put at plus c, or I'm just going to go down the list, a, b, c, d. So I will say at plus b, okay? That's a form of a first degree polynomial. So we need at plus b. So that's going to replace t, okay? Well, now this needs product for sine and cosine. And the angle for cosine in this case is 4t. So our little AB is going to be 4t. So we have cosine of 4t plus, now I'm going to need a factor for sine of 4t, but I also need another first degree polynomial. So I'm going to call it ct plus d. And that will be the form of my particular solution. And now I have to modify this. So I'm going to multiply this by t to some power s, because s will vary depending on what the homogeneous solution was. So if we're solving, we will have a homogeneous case. Any question on this? So you kind of have to remember what are the standard form of first degree polynomial, second degree, third degree, fourth degree. So maybe that's something I want to review. So right, so Liana, you're getting the idea, right? So again, I believe, I strongly believe, it's my opinion, you don't have to agree with me, that the more you practice for any math class, the better you'll understand the problem. Okay, so I try to summarize it in a table, but again, all of these will make sense when you really apply it to an example, okay? So I know there are a lot of symbols flowing around, nth degree polynomial, what the heck is that? But trust me, if you practice, you'll know what the heck is that, right? So hopefully it makes sense. So let me do an example. I want to run through another example, and then we'll probably finish for today. But let's see how we do on the next example. So here's another example I would like to solve. So suppose you're given, let's solve the IVP. So I'm probably not going to finish, but you're welcome to finish for tomorrow, and then we can go over it. Y double prime plus 3y prime is equal to 21 e to the 2t. Okay? So another thing I want to mention is that it never changed the argument for sine and cosine. For example, on the previous example, I said t times cosine of 40. So my argument is 40, the angle, right? So you want to have 40 in your particular solution. Never change it. All right, so having said that, let's give you initial condition on this problem. So y of 0 is 0. Y prime of 0 is 3. So let's see how far we can finish this problem. So hopefully we can finish this for today. So let's go ahead and find the homogeneous solution first. So let me give you a few seconds to digest all of this. Okay, so let's start. So let's find YH. So we have our characteristic polynomial of this. We have r squared plus 3r equals to 0. So this would factor into r times r plus 3 equals to 0. So we have two distinct roots. R1 is 0, R2 is negative 3. Oh, that's nice and neat. So we know our homogeneous solution is going to be C1 e to the 0 is 1 plus C2 e to the negative 3t. Okay, so we found YH. Now let's guess the form for YP. Well, what is g of t? So let's see what g of t involves. Just exponential. So someone guessed the particular solution. So someone tell me what's the form of the particular solution. Driss, do you think you have it? Okay. Thank you. Let's see. Anik, do you have it? Yep. Yep, absolutely. Right? So you can think of 21, the number 21 is a polynomial of degree 0, which is a constant. So we need a constant a and then exponential e to the 2t. Again, you never change the power of the exponential. Now we check. We sit back and look at the homogeneous case. Does my guess appear in my homogeneous solution? So we don't need to modify. So you can think of this as multiplying by t to the 0 power, but that's just 1. So no need to modify this. So, okay. Does this make sense? Okay, I hope it does. Well, now we have to find what is this undetermined coefficient, a, so that means we have to compute its first derivative, second derivative, plug it into the given equation. So yp prime, that's 2a e to the 2t, and yp double prime, that's 4a e to the 2t. Okay, let's plug them in. So we have y double prime. Okay, so if I plug them in, we have 4a e to the 2t, and then plus 3y prime plus 3y prime, that's 2a e to the 2t, plus, no, there's no plus, that's it, is equal to 21 e to the 2t. Right? So you see how both left side and right side have same exponential term except different constant. So that allows you to solve for this unknown constant. So now we have 4a e to the 2t and 6a to the 2t. That's 10a e to the 2t is equal to 21 e to the 2t, which means now I can equate the coefficient on both sides. 10a is equal to 21. A is equal to 21 over 10. Well, let's simplify that. What's 21 over 10? 7 over 5. right? No, no. Sorry. Uh, let's keep it 21 over 10, right? It doesn't simplify it that way, so bad algebra. Okay, so we have our solution. So our general solution to this, so it's going to be y equals yh plus yp. So yh was c1 plus c2 e to the negative 3t plus yp, which happens to be 21 over 10 e to the 2t. Okay, so that's the general solution. But because this question gave you initial conditions, well, that means you have to use them to find C1 and C2. These are the next unknown we have. So you find C1 and C2 by applying the initial conditions. So we were given y of 0 is 0 and y prime of 0 is 3. So let's find the coefficients C1 and C2. So I'm going to go ahead and plug in y of 0 equals 0. So I have 0 is equal to C1 plus C2. And then what else do we have? 21 over 10. Okay, got it. And then second condition, we applied on our derivative. So we compute y prime. That would be negative 3 C2 e to the negative 3t plus 21 over 10 times 2 e to the 2t. And then apply the second initial condition. Y prime of 0 is 3, which means we have 3 is equal to negative 3 C2. And then I can simplify the second term. That's plus 21 over 5. And then this will allow me to solve for C2. So we have two equations that we're going to solve. So let's find these values. If I continue solving this for C2, I'm going to go ahead and add 21 or subtract 21 over 5 on both sides. So that would give me negative 6 over 5 is equal to negative 3 C2, which means C2 is 2 over 5. Okay, so that's nice and neat. So if that's C2, that means I can plug this into the first equation I have here and then work it through for C1. So we have 0 is equal to C1 plus C2, which is 2 over 5 plus 21 over 10. And then kind of play around with this. We have 0 is equal to C1 plus, so if I were to add 2 over 5 and 21 over 10, that's going to be 25 over 10. So that means C1 is going to be negative 25 over 10. And yeah, you can simplify that. I'm just not simplifying it, right? 5 over 2, you can write that down. So we have our solution. So our solution to this initial value problem is going to be y equals C1, which we computed negative 25 over 10. I can simplify that to negative 5 over 2, right? Yeah, that looks right to me. So we have C1, that's negative 5 over 2, plus C2, which is 2 over 5, e to the negative 3t, plus the particular solution, 21 over 10 e to the 2t. So that's how you solve an initial value problem. Any questions? So we finished it. It didn't take us so long, but we accomplished what we wanted to finish. So, all right, this is it for today.